Good morning. Today we are going to deal with congestion management in the restructured power system. So first of all, we need to know what is congestion in the power system. So transmission congestion occurs when the power flow through a transmission line exceed or is about to exceed its safe operating limits, such as thermal limits, voltage limits, and or stability limits. Why does congestion happens in the market? Say, for example, if you take like restructured power system, many generators and buyers submit the transaction. So power traders may push the flows, power flows to some specific corridors. That means transmission line. So renewable generation is sometimes it is variable. Some lines are weaker than the others. So scheduled power is not equal to physical feasible power. So in that time congestion appears. Okay, so sometimes due to the generation, the generation of the renewable suddenly raises. So whatever the scheduled power is not equal to the physically feasible power in that transmission line. So sometimes it is exceeding. Say for example, instead of 100 megawatt, suddenly 120 megawatt is flowing in that particular transmission line. So automatically the congestion will appear. So what is this congestion management? How to manage this congestion? So congestion management is a process by which independent system operator or system operators modify the schedules and control the grid so that no transmission limits are violated. So there will be transmission limits also there. Similarly, like a generation generator limits. So here also transmission system also transmission limits are there. You should not violate. Say for example, that particular conductor can handle 400 kilovolts. Okay, so it may handle little bit more, so plus or minus. But you should not exceed more power transmission in that particular line. Then automatically the line may get heated up. Then losses will be more. So and also sometimes it may not able to withstand. Sometimes possibilities of fault and congestion happens in that particular line. So while minimizing the cost and maintaining the reliability. So what is congestion management? Congestion management is process by which independent system operator or system operator modify the schedules and controls the grid. Okay, so that no transmission limits are violated while minimizing the cost and maintaining the reliability. So what are the main objectives of this congestion management? So if you take like security objectives, which prevents the line overloads and as well as the voltage collapse. So this is the security objective, which prevents the line overloads and voltage collapse. So if you take like economy, minimize the cost of corrective actions. Okay, economic wise, we need to minimize the cost of the corrective action. Otherwise, the cost of the transmission line goes high. Next, fairness, non-discriminatory treatment of market participants. So you should not give any concession to any transmission companies to so non-discriminatory to treatment to all the say retailers can get that much power only. So no concession is given, so they should not get all the contracts or generation companies to generate the power and to transmit that power. They should not given with any discrimination. So non-discriminatory treatment to all the market participants. Next comes the market efficiency. So market efficiency prevents the competition. Okay, and the stability. If you take like avoid the cascading outages. Okay, so cascading outages also that also you need to maintain. So that such that the stability should be maintained. So these are the main objectives of the congestion management. Next comes the what is the role of ISOs in the congestion management. So ISOs in the congestion management, it will monitors the real-time flows via the SCADA, that means supervisory control and data acquisition system. So it will always monitor the real-time power flows. Okay, so checks for the post-market clearing schedule. So whether that, say for example, scheduled power only they are setting or not. That also ISO has to check. Identifies the overloaded elements and selective the corrective action. If any overload happens, so ISO has to be maintain the corrective actions. Okay, so to reduce the generation, and issues the dispatch instruction clearly. So this much power only you need to dispatch, because the transmission lines can handle that much power only. So it schedules the dispatch instruction clearly and settles the congestion charges. So, like any congestion happens, that the transmission company has to pay the charges to the ISOs. So they will not make that into the very few times. But ISOs are keep on monitoring the system, even though if it is more than the scheduled one. So ISOs are monitoring. They will be charged with the penalty charges. Next comes the methods of congestion management. So congestion managements are classified as, first is a cost-free technical methods. So these do not involve payments to the market participants. So if you take like a cost-free, so line switching will be there. So opening and closing of the transmission line to redirect the power. So suppose there will be a sudden increase in the power in that particular transmission line. So we have to redirect the power to some other transmission line. So you can avoid this congestion. So next is transformer tap changing settings. So which alters the voltage and power flow. Suddenly, say for example, if you are connecting an on-load tap changing transformer, suddenly the voltage you can drop. Okay, if the voltage sudden rises there, you can drop the voltage by using the step down transformer like that. So that also you can make, and you can make the power flow. Next, if you take like a phase shifting transformer, so which controls the active power direction also. So phase shifting transformers also will be there. So sometimes what they will do is they will shift the phase. Okay, so phase shifting transformer is used to shift the phase, so which controls the active power direction. Next, fax devices, you can use TCSC, thyristor control switch capacitance, okay, static wear compensator, okay, static compensator to adjust the impedance or reactive power in the line. So that is also possible by using the fax device. Next is series compensation. So which changes the line reactance in the line. So series compensation less used. Mostly fax devices they are using some more. So series compensation very least times they will be using. Next comes the facts example. If we take like a TCSC, what is the main function of the thyristor control switched capacitors? To control the line reactance and reroutes the flows. Next, if you take like a static work compensator and a static compensator, which controls the voltage. Next comes the unified power flow controller, which controls both the real and reactive power. So used first. So this fax devices are used first because they avoid the market disruption. Okay, so these fax devices also used in the system to avoid the market disruption. Next comes the cost-based market methods. If used when technical action alone cannot relieve the congestion. So cost-based market method. So in that generator redispatch. Okay, so which increase the output near to the load and decrease near congestion. Okay, so in between congestion you can read it. So whatever the congestion, whatever the generators that is near to the load, so sometimes they will increase the output of the generator near to the load, such that you can decrease the congestion in the transmission line. Instead of transmitting over some 200, 300 kilometers, so you can identify which generator is near to the load. So that generator, if you increase the output, okay, output, so automatically congestion in the transmission line get decreases. Next comes the load curtailment. So load curtailment reduces the demand in the critical operating zones. Next, counter trading. So in this counter trading, buy the power in deficit area and sells in the surplus area. So wherever the deficit area you need to identify, and you need to sell the power in that surplus area. So you need to transmit the power from wherever not used to the wherever you used more. So such that this also counter trading also can happen in this cost based market balance. So these requires payments and leads to congestion cost. So like this also you can make and maintain the congestion. Next comes the sensitivity based techniques. Okay, so to choose which generator should change the output, the ISOs use the sensitivity factors. That means the generator sensitivity factor, GSF. This generator sensitivity factor indicates how much does the line flow changes if the generator increases its output by 1 megawatt. For example, okay, so generator sensitivity factor indicates how much does the transmission line flow change if the generator increases its output by 1 megawatt. So we are taking the scale of 1 megawatt. So GF is calculated by ratio of the change in the transmission power change in the power in transmission line divided by change in the generation. So higher the GSF means stronger influence on the congestion line. So ISO suggests these generators with a large positive and negative GSF. Sometimes positive GSFs will come, sometimes negative GSF will come. We'll see one example such that you can understand this concept. Generator sensitivity factor. Next comes the transmission congestion distribution factor. That means TCDF, transmission congestion distribution factor. So which it shows that how transaction between two buses affects the congestion line. So this factor, that means TCDF, transmission congestion distribution factor, used to decide which transaction worsens the congestion and allocates the congestion charges. So based on that, if you allocate the congestion charges, so automatically transmission companies will reduce this congestion in the transmission lines. Next comes the optimization based congestion management formulation. So this congestion management is solved mathematically as a, say for example, if you take like objective function, what are the main objective function of this congestion management is to minimize the total redispatch cost. That means cost of change in the power. Total redispatch cost we need to minimize subject to this constraints, power balance constraints. That means generation that equals the demand plus losses. Next, the line flow constraint, transmission line flow constraints, so minimum and maximum operating limits. Next, generation limits, generator limits. That means generator should work in minimum and maximum operating limits. That limit will be specified. Next comes the voltage constraint. So what voltage that in that transmission line we need to operate. So this is an optimal power flow problem. So this problem is like a optimal power flow problem. So based on that, you need to solve this problem and you need to reduce the congestion. Next, solution techniques for the congestion management. If you take like classical optimization techniques, if you take like optimal power flow, the features are deterministic, fast and widely used. Optimal power flow, classical optimization techniques are always used. Okay, so if you take like linear programming method, so simplified DC model, for that it is used linear programming method. Next, the interior point method. Interior point method also handles the large systems. So in this context, this classical optimization techniques are used. Next comes the Meta-Heuristic optimization algorithm. So it is used for complex and non-linear problems. Wherever non-linearity occurs, so we can use for Meta-Heuristic optimization algorithm. So if you take like a genetic algorithm, so it is inspired by based on the evolution, based on the genetic. It uses the selection, crossover, and mutation operation. So it is good for multi-objective congestion management technique. And also, in some problems, they are using this simulated annealing problem also. So the simulated annealing problem, which mimics the cooling metals, how the cooling metal happens. So this problem escapes from the local minima point and moves the problems towards the global minima point. So it works based on the probabilistic search method. Next comes the firefly algorithm. So how this firefly moves towards the brighter solution. So based on that, it mimics the how the fireflies moves to the brighter solution point. That means to the global optimal point. So brightness, which includes that is equals to the lower congestion cost. So if you are utilizing the firefly algorithm in your problem, so that brightness corresponds to the lower congestion cost. So it has to move towards a global optimal point. Next comes the artificial bee colony algorithm. So it is a work based on the like a waggle dance of the bees. So workers, onlooker bees will be there, worker bee will be there, scout bees will be there. So which explores the solution, and queen bee will be there. Okay, so which balance the exploration and exploitation of the problem. So you can utilize this artificial bee colony algorithm also to search for the it will optimal search the food particles, that means honey or nectar in the optimal path. It will always follow the optimal path. So based on that, you can also solve the optimal power flow problem such that you can follow the optimal path. Okay, next comes the particle swarm optimization and teachers learning based optimization. So if you take like particle swarm optimization, swarms moves towards the best solution. Next, if you take like teacher learner based optimization, learns improves via teacher and peer interaction. So you need to select the best students. So we are going to give the training to best students such that students will get good marks. So that is called teacher learning based optimization technique. So feedback based on the feedback from the students, and so teacher will teach in a very efficient manner such that students will get the good marks. That means first rank in the um, exam. So based on that, this teacher learner based optimization works. Next comes the comparison of the this congestion management techniques. So if you take like cost free versus the cost-based method. So cost-free method and cost-based method already we have seen in the enough. So if you take like market impact, cost-free method is mostly used. Market impact is none. So cost-based method affects the prices. Sometimes the congestion happens, automatically transmission companies has to pay the extra tariff to the ISOs. So which in turn they will raise the transmission tariff. So that also it affects the prices in the market. So payments, if you take like cost free, no, cost based you need to pay. Speed is cost free is fast. The cost based is slower. So which is preferred versus cost free is preferred first. Cost based method, if needed, they will apply. If more congestion is happening, then they will apply this cost based method to avoid the congestion in the transmission line. So examples, if you take like cost free method, they are using this fax devices, switching devices, TCSC, SVC, StatCom, and all they are using for this cost-free method. If you take like cost-based method, redispatch method, and curtailment-based method, they are using to for this cost-based methods. Next comes the classical optimization techniques versus the AI-based methods for this congestion management technique, which is based on the features we are going to analyze, which is fast and slow. Like so, if you say take like optimal power flow and linear programming, and in this scale we are taking as classical optimization. So in this scale we are taking genetic algorithm, particle swarm optimization, firefly algorithm. Next, artificial bee colony algorithm. So these algorithms we are comparing here. So if you take like a speed for optimal power flow algorithm and linear power, so speed is higher. Okay, so for this classical optimal for linear program, this means classical optimal for speed is higher. So if you take like a GA and particles, because it has to train the model, so that the time taken will be somewhat moderate. Okay, so that's what speed is moderate. So guarantees optimum, yes, it guarantees local and global optimum. So optimization, what are the main limitations in the optimization algorithm? Is it will give the solution 99% best solution it will give. So 1% it will not. So no guarantee. Okay. So next, if you handle the non-linearity, this classical optimization is limited. So in the GA, PSO, and this like a Firefly method, it is excellent. So computation is cost computation is low. Okay, lesser. So computation time will be high. Okay. Next, real-time use. This classical optimization method is mostly used. So generation so for GA, PSO, and Firefly and artificial bee colony based algorithm, real-time use mostly just used for planning only. So what are the consequences of this poor congestion management? If congestion management fails, next there will be cascading outages will be there, blackouts will be there. Okay, entire system will be blackout. Then again you need to restart the system from the scratch. Next, market manipulation also will be happening. Prices automatically it will goes high. Next, renewable curtailment also will be there. Okay, so we need to stop the renewable system. Sometimes next, whole system get collapses. So these are the main consequences of this poor congestion management. Next, just a small example to understand the congestion management in a better way. So if you take like a transmission line is overloaded. So line limit if you take like the 100 megawatt, but actual power flow is 120 megawatt. So the line carrying extra 20 megawatt more than the safety limit. So this extra 20 megawatt is called the congestion. Okay, extra 20 megawatts, so sudden rise in the demand. So so it is all connected to the online generator. No, so due to the automatic generation control, automatically it will give the signal to the generator such that generators suddenly it will raise the generation to 20 megawatts. So it is not in the safety limit. So 20 megawatt more the power is flowing. So this extra 20 megawatt is called congestion. So system operator must change the generator output so that line flow reduces by 20 megawatt. Okay, so what is the generator sensitivity factor? So generator sensitivity factor tells how much the flows on the congestion line changes if the generator changes its output by the 1 megawatt. For example, for this line, if you take like for generator 1, GSF, generator sensitivity factor, we are taking this plus 0.6. And if you take like generator 2, we are taking the generator sensitivity factor as a minus 0.4. That meaning is generator 1 is having the GSF as 0.6. That means if generator 1 increases by 1 megawatt, the line flow increases by 0.6 megawatt. That means it makes the congestion worse. If the generator decreases power by 1 megawatt, the line flow decreases by 0.6 megawatt. That helps to relieve the congestion. Say, for example, if the same case, generator 2, it is having the GSF as minus 0.4. That means, what is the meaning is, if the generator increases the power by 1 megawatt, then the line flow decreases by 0.44 megawatt, which helps to relieve the congestion. If generator 2 decreases by 1 megawatt, line flow increases by zero point 0.4 megawatt because it is minus 0.4. No, so automatically, if generator decreases by 1 megawatt, the line flow increases the power by zero point 0.4 megawatt. So which makes the congestion worse. So generator it reduces the generator 1. Okay, generator 1 power which reduces the line flow. Okay, if we reduce the GSF of generator 1, which reduce the line flow. If we increase the generator 2 power, also reduces the line flow. So this is the perfect combination to relieve the congestion. So this you need to understand well. Okay. So based on this GSF factor, the generator 1 GSF is 0.6 plus 0.6. Generator 2 GSF we are taking as minus 0.4. So based on that, so if the generator 1 GSF reduces, automatically it reduces the light. If generator 2 increases the GSF, automatically it reduces the light loss. So this is the perfect combination to relieve the congestion. Next, why do we want, say for example, if we want to reduce the line flow by exactly 20 megawatt, so suppose we need to reduce the generator 1 by X megawatt because generator 1 GSF is what 0.6, so which in turn reduces the line flow by 0.6 into some X megawatt. So if we want say for example 0.6 X into X equal to 20 megawatt. So we have to calculate what is X. So X is what 20 divided by 0.6 is nothing but 33.33 megawatt. So reducing the generator 1 by 33 megawatt will reduce the line flow by 20 megawatt because this 0.6 into this X, you need to find out X, no? Into this 33 megawatt will give approximately 20 megawatt. So if you want to reduce the line flow in the transmission by 20 megawatt, you need to reduce the generator by 33 megawatt. Generator power by 33 megawatt. So automatically 20 megawatt you can reduce. If the generator sensitive factor is 0.6, okay, for the generator 1, that you need to do. Say for example, why this generator 2 increase by the same amount. So by using the power balance, what is meant by power balance? So generator must equals the total demand. That means total load. So for example, if you reduce the generator 1 by 33 megawatt, we must increase some other generator by 33 megawatt to supply the load. Because here, there they lose generator 2 also. So check what happens if the generator 2 increases generation by 33 megawatt because here generator 2 GSM generator sensitivity factor is minus 0.4. So just we are assuming that what happens when generator 2 increases by 33 megawatt. So for example, generator sensitivity factor is what minus 0.4. So change in line flow. Say for example, minus 0.4 into that generation factor, that X we are calculated as 33. So if you multiply this, it is coming as minus 13.2 megawatt. So negative means flow should be reduced further, which even better for the congestion relief. So in the generator 2, if you increase 33 megawatt based on this generation factor, GSF factor minus 0.4, so you need to reduce the flow, negative flow by that means you need to reduce the generation by 13.2 megawatt. So which makes the congestion relief better. Okay, so this is the concept behind it. So net effect. So from generation 1 reduction, so you need to reduce, if you want to reduce 20 megawatt in the line flow, that means transmission line. So from the generator 2 increase, you need to increase minus 13 megawatt. Okay, that is also possible. So total change is what? Minus 33 megawatt. Okay, so 20 minus this 13 is minus 33 megawatt. So line becomes fully congested and even as some extra margin also if we do like this. So in practice, the ISO would fine tune this number so total reduction is exactly 20 megawatt. But this example shows the idea. It's not a perfect optimization problem. Just you have to get to an idea to understand how the congestion management they are doing. Okay, so why this minimum cost? Say for example, if you take like in a real market, generator 1 and generator 2 submits the bids for increasing or decreasing the power. So ISO choose the cheapest combination that removes the this 20 megawatt of the congestion. So which is the optimal generator, least cost generator. So in just generator only we can remove this 20 megawatt congestion. So here we are assuming G1 is the cheapest to reduce and G2 also cheapest to increase. So this pair gives the minimum total redispatch cost. Next, what is the final summary from this is, so transmission line overloaded by 20 megawatt. So generator 1 worsens condition, so we need to reduce the power from the generator 1. So generator 2 helps to relieve the congestion. You need, if you want to relieve the congestion, generator 2, you need to increase the generation. Okay, so reduce the generator 1 by 33 megawatt, which removes the 20 megawatt. That is the one option. Or otherwise, you need to increase the generator 2 by 33 megawatt, which keeps the power balance. So congestion cleared at the least cost. So this is just a glimpse of whatever we did.